We'll do it live!
Hi folks, and welcome to an OALabs Patreon exclusive tutorial. So today we're going to be talking about calling conventions, and specifically calling conventions from a reverse engineering perspective. So that's what are you going to see in the assembly when you're reverse engineering something when it comes to calling conventions. What does that mean when you're looking at assembly code? So if you haven't heard that term before, don't worry, stick around. Hopefully we're going to make sense of this by the end of the video. And if you have some inkling of what a calling convention is, but you're not 100% sure when you're looking at assembly what the calling conventions are that are being used, we're going to give you guys some quick tips to help you identify what the calling conventions are when you see a function call in IDA. So stick around for that. We'll try to make it as practical as possible, and hopefully at the end of this you will be comfortable looking at assembly code and determining what calling convention is used for different function calls. So what is a calling convention? Well, this is actually just the description of how arguments are passed to a function when a function is called, and how the return value is passed back to the caller. So that's all a calling convention is. It is a convention, so it is a set of rules that are used when making those calls. And more specifically, if you're developing C or C++ code under Windows, there is a set of predefined calling conventions that are used by the compiler, basically. And so we're going to be focusing on those, but just keep in mind that there are many other ones that we aren't going to cover today in the video. And every standard calling convention out there, whether it be for Windows or for a different compiler, is going to be well documented, because of course you need to know how to implement it. So there's no lack of documentation around this. The point of the video isn't to go through each individual calling convention. The point is just to give you an understanding of what these are, how to recognize them, and just kind of give you a sense of what they look like when you're looking at compiled assembly. So there are different calling conventions for different operating systems, 64-bit, 32-bit, Windows, Linux, different languages. So if you're compiling under Visual Studio versus if you're using the Borland C compiler, they have different calling conventions. Our focus here is going to be mostly on Visual Studio, so Microsoft Windows compiler calling conventions. So that's going to be the focus, because that's mostly what you're going to see in MALWARE. But we will give a couple examples of ones that aren't standard with the Microsoft compiler as well. So like I said, a calling convention just describes how arguments are passed to a function when a function is called, and how the return value is sent back to the caller. It also describes whether the caller or the callee, so whether the code that is calling the function or the function itself, is responsible for cleaning up the stack. So we'll get into that. If you aren't super familiar with how the stack works, calling conventions are a good place to get started, because they have such an impact on how the stack is manipulated in the assembly code that you'll be reverse engineering. So it's good to understand these upfront before you really get into reverse engineering. It's going to help you a lot when you're trying to make sense out of code that you're looking at. Also, compiling conventions when they are implemented at the C layer, so when a programmer inputs a certain calling convention for a function, when the compiler compiles that code down into assembly, the compiler is responsible for translating that convention into actual assembly code. And this is where the terms prologue and epilogue for a function, if you've heard those terms before, a function prologue and function epilogue, that's where this comes from. This is actually code that is generated by the compiler in order to implement the calling convention. So let's take a quick look at what the calling convention looks like. This is a specific one, but we're going to use it as a generic example. So here we have a simple C declaration, C function declaration here. And the calling convention is the cdecl calling convention, which we'll talk about in a minute. But what's important here is that at the source code level, you have a simple declaration, and then when that's compiled, it's translated into this extra assembly code that's added into the compiled assembly. And what this assembly code is doing here is it is responsible for passing the arguments to that function. So here for main, we can see we have 3 arguments, and the calling convention dictates that these must be pushed onto the stack. So the compiler creates 3 pushes to push it onto the stack, and then it also indicates that the caller must clean up the stack, and that's why you see that add ESP at the bottom after the call, because the caller is cleaning up the stack of those 3 arguments that are pushed onto it. So we're going to talk about this more in depth, but just for a concept of what a calling convention is and how it works with the compiler, I just wanted to show you guys this example, and you can keep this example in your mind when we're talking about each individual calling convention. So we're going to start out by talking about x86 calling conventions. There's tons of them, and they're very different. And under x86, calling conventions matter quite a bit. There there's a lot of stack manipulation, and so there's a lot of assembly code that goes along with that. And so if you understand the calling conventions, it's going to be much easier for you to analyze x86 assembly code. So the few things that we have to keep in mind here when we're talking about x86 calling conventions: all arguments are expanded to a 32-bit size, so a D word. Of course, this is because the processor, all the registers, etc., are expecting D word sized chunks of data. So all arguments must be expanded to D words when they're compiled to assembly. The return value is also expanded to a D word size, and the return value is always returned in the EAX register. So you guys have seen many different tutorials when we're talking about API calls, and we're always looking at the EAX register for the return. That's why, because under x86, the return value is returned under EAX. If it's a 64-bit size word, so a keyword, it's 2 D words wide, then it's returned in EDX and EAX, 2 registers, and EDX is the most significant bytes. So it's important to keep that concept in your mind when you're looking at return values. Of course, if the return value is a structure, then a pointer to the structure will be returned in EAX instead of the immediate value. So there's a couple different caveats here. There's more actually than we have listed here, which you can look up in the MSDN documentation for calling conventions, but these are the basics just to get you started. Also, the registers ESI, EDI, EBX, and EBP are non-volatile. That means that they're not changed by the function call. The other registers can be changed by the function call, so you can't rely on those being constant, but you can rely on these ones being constant when you call a function. You're not going to have to save them yourself. You can rely on the function to save them for you. Also, like I said before, MSDN is your friend. We're not covering everything here. Of course, you've noticed we don't even talk about floating point numbers. We're only really talking about integers here. So there's a whole other set of conventions when you're passing floating point numbers to functions, which you're going to have to look up for yourself. So in a nutshell, that's x86 calling conventions. These are basic things that are pretty much always going to be true for every standard calling convention, unless you create the calling convention yourself, in which case you can do whatever you want, but you have to be consistent with it. So the first and most common calling convention is the CDECL, CDECL calling convention. The reason why you're going to see this everywhere is because this is the default calling convention for C and C++ code. So you pretty much see this everywhere. It's probably one that you might be familiar with if you've done some reverse engineering. You've probably seen this before. So all the arguments are passed on the stack, the push from right to left. So that means that the first argument, arg0, is going to be the last thing pushed on the stack. It's going to be closest to the function return. Also, the caller is responsible for cleaning up the stack. So that means that the function doesn't have to care about cleaning up the stack. It's the responsibility of the code that called the function to clean the stack. This is important because what this does is it makes it possible to pass var_arg arguments or create variadic functions, if you've heard that term before. What does that mean? That means you have a function with an undetermined set of arguments. So if you're familiar with, say, sprintf or a format string call, where you have the format string and then you have a number of arguments that are passed, and that number of arguments is variable. So we call these var_arg functions. These functions are only really possible with a calling convention where the caller cleans up the stack, because of course the function that is called has no idea how many arguments there are, right? The whole point of the var_arg is that there can be a variable amount of arguments. The only piece of code that knows how many arguments there are is the piece of code that calls the function. So thus it's the responsibility of that code to clean up the stack. Don't worry if you don't quite grasp that yet. I'm going to show you a bunch of examples in IDA, and hopefully that'll clear it up for you. So as an example here, we have a simple hello world program compiled in C. We have 3 functions here. We have hello1, which just prints hello world 1. We have adding numbers, which will take 8 arguments, add them together, and return the result. And we have adding numbers variadic, which is a var_arg or variadic function. You can see here we have an undetermined number of parameters. And this function functions very much like adding numbers, except the first argument tells you how many numbers you're going to add, and then the second set of arguments is however many numbers you want to sum. So this can take any number of numbers and sum them up. Here in our main, we call hello1 just to print out hello world. Then we use adding numbers to add up 1 to 8. And then we use adding numbers variadic to add up numbers 1 to 8 as well. And of course, the first argument is the number of arguments that you're passing to it. So we've compiled this here, turning off compiler optimizations, but leaving everything else standard. And let's take a look at it in IDA. So here's our main in IDA. Here's our first call. So this is our call to hello world. And you can see it doesn't take any arguments. So you don't have any arguments being passed here. You don't have any stack cleanup. This is an example of a function where there's no arguments. So you don't necessarily know what the calling convention is for this, but it doesn't really matter because you're not passing arguments to it. The next function here is our add numbers function. And it takes 8 arguments, and you can see each one of these is being pushed onto the stack here. So it's pushing 8 arguments onto the stack. And you can see afterwards, it's clearing the stack of 8 arguments. So 20 hex, if we press H to convert that into decimal, is 32. And if we pull up our calculator here, if we do 32 divided by 4 bytes in each argument, you're going to get 8 arguments. Of course, we're in x86, 32-bit mode, so each one of these arguments is 4 bytes. You have 8 of them, so that's going to be 32 bytes on the stack here that are being removed. So looking at this, we have arguments that are pushed onto the stack. We have the caller cleaning up the stack. What does that tell us? It tells us most likely this is a cdecl calling convention. If you hover over the function and press Y, you can change the type. And you can see here, IDA has already identified it as cdecl, right? So this is how you identify the calling convention by looking at the assembly. If we take a look at the function itself, we're going to see a few more interesting things here. So here inside the function itself, we have what we call the prologue and the epilogue. Now in this case, because the caller is taking care of the stack, it's clearing the stack for us. And because the variables are pushed onto the stack, the prologue and epilogue don't have to do anything. All they have to do is save the base pointer and then restore it once they return. So in a nutshell, that's cdecl. It's very easy to see the format, especially when you look at the caller and you see that the caller is responsible for cleaning up the stack. Now, if we look at our variadic function here, let's click on it and press Y. You can see that IDA has not identified this as a variadic function. It thinks that the function only has 1 argument, so it hasn't been able to identify that. And if we look at the setup with the arguments, we're pushing 9 arguments onto the stack. Of course, these 8 here are going to be the arguments that are going to be summed, and then 8 here is telling the function how many arguments are actually being passed. Now, of course, looking at this assembly, we wouldn't know that. What we're going to have to do is we're going to have to look at this function itself to figure that out. Let's go into the function here, and it's going to actually be easier to see this if we turn it into graph mode. So I'll press space, and let's label this up a little bit so we can see what's going on. So here we have our arguments. We know that this is the number of arguments, so let's label this as arg length. And we know that this is our first argument here. Now we know, because we've looked at the source code, that there's actually 8 more arguments being passed. But right now, let's just label this as arg1, and then we'll see, what's happening here. So let's press N to name it. We'll call it num1. So it's the first number that's being passed to this function. Now let's see what actually happens here in the code. We have our prologue here where we save the base pointer. We also see we subtract 0c, so press H to turn that into a number. That's 12. We subtract 12 bytes from the stack. So that means each argument, of course, is 4 bytes. So 12 divided by 4 is 3. So this is 3 arguments. So we know we're going to have 3 local arguments in this function. And of course, IDA has helpfully shown us these 3 arguments up here. Next thing we do is we move 0 into one of those arguments. We can't really figure out what's going on there yet, so let's skip over it. Next thing we do is we use a load effective address of num1 into EAX. So EAX will have the address of the num1 argument, and then we move that address into var4. So let's name var4 as var pointer to arg num1. right? So this actually has the address of that first argument. So let's move on here. We move 0 into var 8. I'm not sure what that does yet, so let's keep going. We move var 8 into edx, and we compare that against the length. Okay, so maybe this is some sort of counter. Let's see what var 8 is doing. It is a counter. So we can see here in this loop, var 8 is moved into ECX. We add 1 to ECX. ECX is moved back into var 8. So this is some sort of counter, and it's compared against the number of arguments. And if it is equal or greater than, we end the function. So this tells me that this is going to be a var arg counter. So we're actually going to count off however many arguments there are. Once we're finished the number of arguments, we're going to go and exit the function. So this must be the meat of the function here. This must be where they're actually doing stuff. Let's clean this function up a little bit more. We can actually group these together here because we know that this is just adding 1 to var arg count. So that's just plus equal 1. And let's group these together. We know that this is just a conditional that compares var arg count against arg length, and if it's greater than or equal, it jumps here. So let's group these up. So this is if var arg count is greater than or equal to arg length. So if it's greater than or equal to, we jump here. If it's not, we come here and then we add 1 to count and we continue the loop. So let's see what they're actually doing here. They take the address of the first variadic argument, they move it into EAX, they add 4 to it. So remember, 4 bytes per argument. So that must mean that they're incrementing to the next argument in the variadic function. So they're incrementing the argument by 1 here. So let's add a little comment, get next argument. Then they move that address into ECX. So this is the address of the second var arg argument. And then they move var c into EDX, and they add EDX, and oh, they minus, this is very interesting. So this is some strange assembly here. So they actually they minus 4 from that address, and then they take the value within it. This is actually get value of previous argument. Right? So they actually increment to the next argument, but they use that minus 4 to get the previous argument, and then they add that to EDX. So what is EDX here? It's being moved into var c, and it looks like var c is set to 0 here. So this must be the sum of all the numbers. So let's label that now, var sum. Okay? So they add the value of the first argument, because of course they went to the next argument, but now they're going back. So they add the value of the argument to the sum. They move EDX back into the sum, and then they continue the loop here. Once they're done with the loop, we come over here, they zero out the address of the pointer to argnum1. I guess that's just some sort of cleanup here. Then they move the sum into EAX. And remember, in the calling convention, EAX always is the return. So return sum, okay? And then they return. So now that we figured out what's going on here, we can tell by looking at this code here that there must be multiple arguments that are passed here. So you can see we weren't able to tell that this was a variadic function without having to actually look at the code. And that's a common theme. Now, IDA has a template for this code, and it will be able to determine that this is a variadic function if you use the decompiler, if you have the decompiler. But if you're only looking at the assembly here, you're going to have to do a bit of work to identify this loop and figure out, oh, this is in fact multiple arguments. So if you click on the function, you press Y, you can redefine the second argument here, ... telling it that it is a variadic function, and then you can click OK. All right, now that hasn't really done very much for us here. It's just a reminder to the analyst that this is a variadic function. If, however, we were going to decompile this using the decompiler, we can do that now, F5. You can see that IDA has identified that this is a variadic function, and they've added the VA start and VA copy functions here. If we look at our source code, of course, we have the VA start function here. So that is how to identify a variadic function and how to identify the cDecl calling convention. Again, remember the cDecl, the caller cleans up the stack. That's the giveaway for you whenever you see this. Between this section of code and this section of code, you wouldn't be able to determine that this is a variadic function. You would have had to actually looked at the function, done the analysis to determine that it's variadic. And how do you know it's variadic? Well, you know that because they're iterating through the number of arguments that are passed, and the first argument determines how many arguments that are being passed. So without doing that analysis, you wouldn't have been able to determine that it was a variadic, but you could have determined that it was a cDecl call by looking at the fact that they clean up the stack here. Okay, so that concludes our first part on calling conventions. If you're a Patreon subscriber, just scroll down a bit and you'll find links to our other tutorials on calling conventions, including fast call, this call, x64 calling conventions, etc. If you're watching this on YouTube, I encourage you to subscribe to Patreon, where you'll find access to all these other calling convention tutorials that we put up there. I hope this is helpful for you guys, especially if you're getting into reverse engineering. Personally, I think understanding calling conventions is a key to unlocking a lot more understanding about what you're looking at when you're looking at assembly code. And hopefully with this tutorial here, we've given you a few tools that you can use to help further your reverse engineering and make it a bit easier to make sense out of the assembly code that you're looking at in IDA. So with that, look forward to seeing you in our next tutorials, and I'll see you on Discord.